Oh, hi, welcome. This is chapter one lecture. In chapter one, I have two parts, part A and part B. In other words, there will be two lecture recording. Allow me to share my screen where you will see the PowerPoint slides and my whiteboard. You should have a scratch paper piece of paper so that you take the notes as we go along with the lecture. You should be seeing right now my screen, and on my left is a whiteboard where I'll be showing some examples if need be. And on my left, I will be running the PowerPoint slides. So chapter one is basically the introduction to matter, energy, and measurement. This is a pretty straightforward chapter, which I believe you can read and understand the material. It's something you may have covered in introduction to chemistry if you took the course, or some of you may have taken the challenge on Alex so that you get enrolled in 10KM1. So let's see, I'm just going to briefly break down, define these terms highlighted on the title for chapter one. Matter is simply anything that has mass and occupies space or has volume. Towards the middle of the chapter, we look at energy. Energy is basically the capacity to do work. We'll define that. And there are two most important type of energy you need to commit to your memory, the potential energy, kinetic energy. And lastly, we will look at the concept of measurement. When we say a measurement consists of two things, a number and a unit attached to it. Otherwise, a number will just be meaningless, Let's see. The word chemistry, before we proceed, chemistry is simply, all right, chemistry is simply study of what? Of matter and its transformation. This simply the definition of matter. And earlier on, I defined this term matter. We look at it momentarily. This is simply what concerns matter and its properties or matter. In this case, anything you can think of, the text, the pen, eraser, so long as it has volume, all right, and has mass. Anything that has, this is just anything that has mass, all right, underline the word mass, and volume. Anything that has mass and volume, that means occupy space, is what we call matter. Properties, this is just simply the characteristic features used to describe matter. We'll look at it later on. In chemistry, we consider chemistry as the central science. I don't want you to think that what the slide you see here is only for, the definition of chemistry as the central science. In other words, in chemistry, we use in all fields. For example, a nurse will need chemistry, a doctor will need chemistry, all right, a physicist will need chemistry, all other field, all right. This is where chemistry is. It encompasses energy, power, chemistry, medicine, and technology, all right. This is just to illustrate that chemistry is considered as the central sense. I had earlier on divine matter. Matter is anything that has what? That has mass and takes up some space, or if it has a volume, you see our volume there. That's how you define matter. You should be able to do it, define matter. This is just the diagram you see here is illustration between the composition of matter that can consist of elements or molecules. We'll see later on the difference between atoms and molecules of different compounds, Take home message here is that you should be able to define matter. You should be able to define matter, and matter can be classified. All right. According to either the state or composition, according to either the state or composition. Remember, there are what? Three states, all right? There are three states of matter. These are one, solid state, there is a liquid state, and then there is the what? The gaseous state. There are three states. Even though we have five, we're not going to look at the other two. We have plasma, which is not for us. So these are the three states you should know. And apart from just classifying that, you should know the properties as well. Now, classifying matter is in terms of composition. Gonna look at the composition in terms of mixtures, homogeneous mixtures, heterogeneous mixtures, and so forth, right? So let's take a roadmap, go down with me on classification of matter as solid, liquid, and gas. Having pictorial representation of molecules or atoms, you should be able to draw a parallel between the arrangement of molecules or atom in solid state, in liquid state, or in gaseous state. This is representation of the three states of matter using H2O, basically water, in solid state, in liquid state, and in gaseous state. Now, chemists use color coding to depict or portray the atoms, all right? Here in this diagram, right here, the red represent oxygen, the white spheres represent hydrogen. Recall from the molecular models, if you did experiment on models, you may have had an opportunity to build molecule, and hydrogen are always white, oxygen's red, and you will see some other atoms down the line. But point here is there are three states of matter: solid, liquid, and gas. And given the diagram, if you look at the gaseous, in gaseous states, the intermolecular space is the largest in gas. In liquid, molecules are able to roll over one another. They can move around, but in solid state, they are rigid or fixed in one spot or one position. So if I were you, I'll have 4 pi 6 index card, draw the parallel between classification of matter as solid, liquid, or gas. Know that. Okay, let's move on to classification of matter based on composition. This is where we look at mixtures, all right? And there are two types of mixtures, heterogeneous and homogeneous. When we say homogeneous, all right, did I get right? No. I need to have E right here, homogeneous mixture. all right? This means from the word homo, it is means one phase, all right? This means you have more than one substance in a mixture, but it appears as if it is only one substance. For example, I may have liquid H2O, all right? I may have, you cannot see from there, this is liquid H2O. If I dissolve table salt, sodium chloride, it will dissolve. It will look clear. It will look like as if it is just pure H2O, but in essence, it is homogeneous mixture. That means you have one phase. Example here, by the way, examples include air, all right? Air in this room consists of nitrogen, all right? There is CO2, there is probably gaseous H2 in the atmosphere and other trace gases in the atmosphere, but they all form one uniform mixture we call heterogeneous. We can also have here salt, all right, salt plus H2O, all right, this is an example of homogeneous mixed. It means you mix or you have more than one mixture, but they appear as if there is only one phase. You have only one phase. Heterogeneous, all right, when we say heterogeneous here, heterogeneous mixture means these got two or what more phases. All right, you see two or more layers. E.g., you can have what oil plus H2O. You try to mix the two. At some point, it will start separating. We can have here what sand, all right, plus H2O. All right, concrete, for example, those are just few examples of heterogeneous. You should be able to define or differentiate between homogeneous and heterogeneous so that when you are given an example, you should be able to classify it as either what? As either heterogeneous or homogeneous, heterogeneous, homogeneous. And then there is the element, we can classify substance as either elements. Elements, all right, these are the fundamental building blocks, elements, all right, the simplest part of matter. Element can have this, e.g. Sodium on the periodic table, hydrogen, helium, oxygen, fluorine, potassium, all right, calcium, iron, just to give you a few examples on the periodic table. And I want you to start learning the element on the periodic table. I meant to share with you the, all right, let's see if I have the periodic table here. These are a few elements, all right? These are few elements. I mean, you see here, elements on the periodic table: hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, beryllium, okay? I'm going down, but you know, elements are arranged from left to right: boron, carbon, nitrogen, oxygen, fluorine, neon, all right, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton, and so forth. These are the elements on the periodic table, all right, which is part of classification of matter you see here. All right, when we say element, you should know what we are referring to. All right, you should know what we are referring to in terms of classification. Now, when two or more elements combine in a specific ratio, they form compounds. Remember what I say here, these are the building block of compound. Compounds, all right. Pure compounds, we have what? H2O, for example, consists of 2 hydrogens and 1 oxygen. It's a compound. This is a compound, calcium carbonate, all right? This is calcium carbonate made up of 1 calcium, 1 carbon, and 3 oxygen, specific ratio. CO2, this is a compound. So you should have a sense of what consists of a compound. It's only that these elements, I mean, compounds can be separated into pure elements by chemical means. These two heterogeneous can be separated into pure substances by physical means, which we will see later on. This is just a flowchart. Please learn, commit to your memory so that you can classify matter based on the 4 terms: homogeneous, heterogeneous, element, or compound. All right, when given a compound, should be able to classify. All right, so here are classification of compound distinct properties. All right, 2 types of substances, pure substances, elements and compounds. All right, pure can either be what? You want to break it down. These will be compounds right here, and here are elements. We can physically say, I mean, chemical separation. Chemical separation can separate that into pure elements. Compounds can be separated into pure elements using chemical means. For example, H2O, we can separate oxygen from hydrogen by passing electric current in a process called electrolysis, all right? So substances cannot be broken down, it cannot be decomposed into simpler substances. However, compounds can be decomposed to simpler substances, all right, by chemical means. Here is an example of H2O. We can separate that into hydrogen and oxygen. We get that. So please read more on that. You see that. Now the atoms, all right. These elements, this portion on the period on the flow chart right here, elements are made up of atoms, and they are the building blocks of element of matter. Atoms. Let me just define this so that you know the difference between compounds, element, and atoms. I can simply say these are we can say simplest form of matter. It is the indivisible. That means you cannot, and indestructible, you cannot destroy part of matter. You can just simplify or simply define atom as the indivisible and indestructible part of matter. You will never destroy, all right? Even though later on, we will learn about the subatomic particles. That means what made or what makes up atoms. Are electrons, there are protons and the neutrons, subatomic particles, and though we say here, they are the simplest, indestructible part of matter. So here, each element on the periodic table is unique, all right, because of the uniqueness of atom. For example, an atom of sodium has 11 electrons. No other element on the periodic table will have its atoms with 11 electrons. Therefore, we say that each element is made up of a unique, because of what? They have unique properties. Unique number of electrons, unique number of, unique number of electrons and protons. Of course, for neutral atoms, we talk of also same or unique number of electrons. So compounds are made up of two or more atoms of different elements. For example, here is a water molecule made up of one hydrogen. Remember, I say white sphere represent hydrogen atom. The red sphere represent oxygen atom. So this is water molecule. Ethanol carbon is always black sphere, right? So in ethanol, we have two carbons, and I see there is 1, 2, 3, 4, 5 hydrogen and 1 oxygen. This is just illustration of what constitutes or what makes up compounds. Compounds are made up of two or more atoms of different elements. This is just illustration of the elemental composition of the human body, what consists of mainly 90% of the human body is made up of three elements. All right, this is human body, and you see there's oxygen, carbon, and hydrogen. These are just other elements. All right, on the art class, this is just few elements which I will not ask you to memorize the numbers you see here. What I want you to do is learn the first in order for your life to be easier down the line. Please learn at least the first 50 elements on the periodic table, just naming them, writing their correct chemical symbols, writing their correct names, all right, and knowing the position on the periodic table. Number 1 is hydrogen, number 2 is helium, lithium, and so forth. Please use 4x4 index card, or you can look for, all right, you can look for some free apps on either Play Store or App Store, so that you can do it. You can learn those elements on the periodic table, the names as well as their chemical formulas. This will not help you. Table 1.1 is just a table. Some few common elements does not mean this is what you need to pay attention to only. For exam, for a quiz, or for homework, it's just illustration that, the chemical symbols, the names, all right, and just explanation of the uniqueness of the names. Some names, they have Latin origin, all right, some have Greek symbol, all right, some elements, symbols have their first letter and the second letter, all right. Please, always the first letter is capitalized. I don't want you to keep me caution as CA. This is California. I don't want that. Or for scandium, you write SC. This is Ca. For scandium, it is S and C. I don't want to see sodium SC. This is not applicable. You just have to write Na. So learn how to write the chemical symbol in a correct way. It should be, okay? It should be. So if you look at the chemical symbol for some element on the periodic table, it has some Latin origin, all right? Kalium for potassium, for example. Don't worry why potassium doesn't have P. I know some of you may think that this is for potassium. This is phosphorus, all right? You see here, but because of the Latin origin kalium, natrium for sodium, number 11 on the periodic table, all right? Just in case you're wondering why some elements have unique chemical symbols or names, it has to do with their origin. Some elements have names associated with the scientists who discovered them. For example, polonium, or is for Poland, that's the foreign country, or the Einsteinium for Albert Einstein, all right? So these are just few elements on the periodic table. Please learn the first 50, the chemical names and the chemical symbols, the chemical names and the chemical symbol, right? Okay, let's switch gears to composition of matter. Looking at the compounds, for example, here H2O, the compounds, all right? Elemental composition of compound is always the same. For pure compounds, we call this law of definite composition, which is attributed to Joseph Proust. He was a French chemist. So the law of here, let's see first, law of definite what? Definite composition, all right, or constant. Sometimes we call this constant composition, or the same thing as law of definite composition. This states that, all right, this states that elemental composition of a compound is always the what? The same, always the same. Elemental composition of a compound is always the same, no matter the source. Example here is H2O, no matter the source, the elemental composition of H2O consists of 2 hydrogens and 1 oxygen. Whether it is synthesized in the lab or it's sourced from the nature, the composition will always be the same. This applies to other pure compound as well. This law is associated with a French chemist by the name Joseph Louis Proust, Proust. All right, Joseph Proust, who lived between 1754 to 1826. The years doesn't really matter, but you should be able to, all right, know who is credited for this law. He was working with calcium carbonate, and every time he did the elemental analysis, he ended up with the same mass of each element in that compound, hence led to what we call the law of definite composition, and Joseph Louis Force, a French chemist, is credited for this. Sometimes down the line, we'll also look at other scientists, and you should be able to tag a scientist to the law or scientific contribution. Dimitri, for example, credited for the periodic table. We'll see that. Okay, we'll see that. So note the definition of what the law of definite composition, what it states, and who is credited for that. That means that the relative number of atoms of each element in the compounds is the same in any sample, no matter where it is. Okay, no matter where the source is. I talked earlier on about the mixtures, all right? There are two types of mixtures: heterogeneous mixture, homogeneous mixture. Homogeneous mixture is also called solution, all right? And in solution, we'll see in chapter 4, I believe, consists of what? Solute, all right? We're gonna see this plus solvent. Solvent, this is a minor component, right? And this is a major component in a solution. So if form a uniform solution, we call that homogeneous. Homogeneous. Please learn to list, right? You can ask your friend Google to give you examples of homogeneous. If I look at here, this looks like calcium, copper sulfate could be hydrated or anhydrous. Yes, it's hydrated. Dissolving this, it's soluble, okay? It is soluble, forming a uniform solution. We call this homogeneous. This one, in case you're wondering, it looks like, countertop, granite countertop. It is heterogeneous. I see there are black spots and brown spots. It's not uniform. We call this heterogeneous mixture. Heterogeneous mixture. Please, like I say, please make your own notes. List a few examples, more examples on homogeneous mixtures, heterogeneous mixtures, so that when you are given in an exam, for example, that which one of the following is heterogeneous, then you will know. Or how will you classify this compound or this substance, for example? You should be able to be well-rounded. All right. Moving on to section 1.3, properties. All right. Before we look at the two types of properties, I want to define property. We call this just characteristic feature. This is characteristic what feature used to describe, all right, describe matter, matter, all right. This is something characteristic feature. This is solid, all right, physical state. You cannot see, this is my, I have my calculator with me here, and it's a solid, it's black, you know, the color, I'm describing it. So anything you use to describe matter is called a property. All right, and properties can either be what? Physical or chemical. A property can either be physical or chemical. We'll see each one of them, all right? A physical property is something you can observe without changing the physical, the chemical makeup, something you can measure without, all right, changing the chemical makeup of a substance. For example, All right. Example is the color. All right. As I showed you earlier on, this is a plug calculator. All right. Sometimes I've seen pink, but mine is black. So I'm using color to describe that. All right. That cologne smells good. You know, I'm not changing the chemical makeup when I say, you know, describe the smell of a cologne, all right, or a spray. I'm just describing the substance. Density, all right. You don't change the chemical makeup by determining the density of an object. We can determine the density of liquid H2O in a lab without necessarily changing the chemical makeup of what? Of water, okay? Density for water is always 1.00 grams per ml. Does not change the chemical makeup. It will always be, all right, we can always measure without changing the chemical makeup. We can observe without changing the chemical. Observe means you can look at. You can measure without changing, all right? Melting point, yes. Ice cube can melt at 0 degrees Celsius, all right? Water can boil at 100 degrees Celsius, normal boiling point. We don't change the chemical makeup, all right? If I try to break my iPad pencil, it's hard, I can break. So I'm just describing the property of my, all right, the property of my iPad pencil that I cannot break. I don't want to attempt that, but you know what I mean. You cannot break a nail, but you can break a toothpick. Those are just physical properties. We can observe, we can do it. We can measure without changing the chemical makeup. This diagram, don't worry about this diagram. It's just came here. It falls under the separation of matter, separation of mixture. We will look at that later on. It's a distillation apparatus. Let's look at the chemical property. Chemical property has to do with the chemical reactivity of a substance. Flammability, flammable. This has to do with the, you know, chemical reactivity of substance, corrosive. HCl, concentrated hydrochloric acid, very corrosive. All right, that describes the chemical property of hydrochloric acid. I can say, right, I can say H2O is non-flammable. That means it has have to perform some chemical reactivity, try to ignite, and if it doesn't ignite, it's said to be non-flammable. It has to do with the chemical reactivity of H2O. Gasoline is flammable. It has to do with what? With the chemical reactivity, chemical property of gasoline. Hydrogen is combustible, right? Those are chemical properties. So anything that has to do with changing the chemical composition of matter when you measure it out in order to give a different substance is called chemical property. If you burn gasoline, you will end up with something else. It will not remain gasoline. One common chemical property is flammability. So when you say flammable, able to burn in oxygen, right? You see that quite often. See that quite often. Now, those are the two types of properties you need to learn, read more in the text, make your own notes. Properties also can be either classified as intensive or extensive. There is what we call here, maybe drawing a parallel between intensive and then extensive. Intensive, extensive. Here, independent amount of matter in it, regardless of how much you have in there. All right, we call that extensive. For example, here, color is an extensive. No, I mean intensive. If I have, a cream apple, slide it into two, all right, each piece will still remain cream. So it's independent of the amount, doesn't really change. Density, for example, here, all right, density, regardless of how much H2A you have, still density will be the same. It doesn't depend on the amount. Likewise, boiling point of H2O, whether it is 10 ml or 5 gallons, still boiling point will be 100 degrees Celsius, 100 degrees Celsius. So intensive properties are those independent on the amount, underline the word amount. Of course, the extensive properties, all right, they are dependent, all right, here, depend, all right, depend on the amount, all right, these depend on the amount of matter we have. Example here is area, all right, I hope you can see that, area, okay. If I can determine the area of my calculator length times width, all right. If I have two or three calculators stuck side to side, all right. The more I have, the larger the area will be. Therefore, area is a function of, it depends on the amount you have. Mass, for example, all right. All right. It depends on the amount. In the lab, all right, in the lab, if the direction called for 1 gram and you weigh or mass out 10 grams, of course, you will have more matter in 10 grams compared to 1 gram. So mass is an extensive property. Volume is an example, goes to volume, all right? Volume, the more you have, the more volume you have. Of course, depends on how much you have, mass, volume, and also the energy. See that energy earlier on. This is just a learning check. You have the PowerPoint slides, learning check. When we say that lead is denser than metal, than aluminum, sorry, are we talking about extensive or intensive? When we talk about density, the key word here is density. Is it extensive or intensive? This is B, intensive, because of what? We are referring to, it doesn't depend on the amount of lead. It's just the density will just be the density. All right. So you should be able to classify, all right, a property as extensive or intensive. So the correct answer is B, intensive, extensive, intensive. Please make your own notes as well on extensive and intensive properties. Now, let's switch gears to types of changes when matter change its states, or when the state of matter is changed from one state to another, all right, we talk about physical change or chemical change. Physical change or chemical change. Let's see here. There are two types of changes you should learn, memorize, and commit to your memory. These physical changes do not change the composition of matter, all right? It does not change. So you have A going to A, it does not change in physical, all right? Physical change here. And if you want to know the type of physical changes, most common is change of state. When we say change of state, I'll say here, let's say change of state, we have gas, we have liquid, and then we have solid. I want to highlight this. It may look simple, change of state. On my my whiteboard, if you look at the flow chart, the diagram, look at the diagram. I have this going up here, and then I have coming down here. I have one going up there. I have down. There is one going from solid to liquid. All right. There is one change of state from solid all the way to gas without going through liquid state, and from gas to solid without coming through the liquid state. Those are changes of state. From solid to liquid, we call these melting, all right? And then we call this freezing. Everybody knows freezing. Change of state from liquid to solid. And then we have condensation. We have vaporization. Exchange of state from liquid to gas. And then there is a special one from solid to gas without going through the liquid state. We call this sublimation. And we call this deposition, coming straight from gas to solid without going through the liquid state. So when you look at here, change of state, this is what I'm referring to, and you should know, all right? You should know here is the sublimation, all right? Everybody knows sublimation. This is N, all right? Sublimation. So here, temperature is a result of temperature. Now, physical or chemical changes are a result of new substance being formed, combustion, for example, oxidation, decomposition. Those are chemical change. Even digesting pizza, that's a chemical change. Rusting, that's a chemical change because you end up with what? New substances. So when you digest pizza, it's gone forever. You end up with new substance. All right. Combustion, burning, oxidation, decomposition. All right. Fermentation, for example, when you ferment sugar, all right, you end up with new substances. So those are just few changes. All right, there are physical changes which I've described earlier on: liquid water, solid water. All right. There's a diagram I used earlier on. This is just illustration of chemical change, chemical reaction which take place. Now, is the following change physical or chemical plants make sugar from carbon dioxide and H2O. How will you classify plants making sugar from CO2 and H2O? A, chemical change cannot be determined without additional information, neither physical nor a chemical change, all right? Physical change, I think it is a chemical change because we are making new substance. We are making sugar from, or plant is making sugar from what? Carbon dioxide and H2O, carbon dioxide and H2O. Earlier on, I mentioned some diagram on simple distillation apparatus, and let's look at the separation of mixtures. I think it's experiment number 3. If you are taking the lab this semester, or if you took lab last semester or previous semester, you may have done experiment on separation of component of a mixtures. Mixtures can be separated into pure substances. So if I do have here, let's have a diagram here that are mixtures here. Can here should be, sorry about that. I want to say this to be just matter. Matter can be classified as mixtures or what? Pure substances, which means these can be what? Separated physical separation. You can be separate mixtures into pure substances by physical separation, of which we have evaporation, you know what that means. There is the filtration. It's a technique you should know. In organic chemistry, you'll see this distillation like that. And then there is a thin layer chromatography, TLC, or just chromatography technique, all right? There is vacuum filtration, we see that as well. These are just few physical separation which can be used to separate matter into pure substance. Filtration, in filtration, some substances are separated from liquid. You pass the liquid through some filter. So here, what goes on here, let's say here is the filter, and then there is the solid here. And then here, it's important to understand this is called filtrate. Filtrate is the liquid portion which goes through. We separate solid from liquid by physical mean. By physical mean, passing the liquid through a filter. This is an example of filtration apparatus. There is the ring, goes hooked up to some ring stand. There is the funnel. We call this funnel. And then there is the filter paper, filter paper is just act as a sieve, all right? Liquid substances will go through. We call this the filtrate, get to know the term, and the solid will remain on the filter paper. This is the filtration apparatus. You can check on YouTube more about filtration. Distillation, this is a common separation technique in organic chemistry. You'll see this, it just uses the difference in boiling point. For example, methanol, all right, has a boiling point of 78 degrees Celsius, and H2O has a boiling point of 100 degrees Celsius. These are just boiling points. We can separate the two. We can separate the two into pure substance by employing what we call distillation apparatus. So here is the mixture of the two. Once the temperature reaches 78, only the methanol will flow through. This is called the condenser. Cold water in so that the gaseous liquid substance will condense. You'll collect, right, or we'll collect methanol. Once the temperature rises up above 78, anything which will come through the condenser will just be H2O. This technique uses differences in boiling point of substances to separate them into, to separate homogeneous mixture into pure component. I will just leave the chromatography. This you may use it down the line, all right, especially TLC. This is just uses the different mobility of substance through some porous material. I'll just leave at that. Please read more about separation of what? Separation of mixtures into pure substances. Make your own notes. You will need those in the lab as well. In the lab as well. Well, this is almost the end of part A. I want just to briefly go through the energy, all right, before we take a break, and then we'll come back again for the last part of chapter 1. Energy, all right, you should be able to define energy, and energy is simply, all right, energy, this should be lowercase, should have that. Energy is simply capacity, TCC, to do work, capacity to do it, to do work, or this is ability to do work, all right. This is just the definition of energy. You should be able to define energy. You should be able to define energy. And there are two most important types of energy. There is the kinetic energy. This is kinetic what? Kinetic energy, kinetic energy, which is simply defined as energy what? Energy in motion, energy in motion. It's N here, energy in motion. It is the energy possessed by moving object. If someone is moving on your, if you stand on the way of somebody, somebody might knock you off because of the energy possessed, right? That moving some, right? Now, there is we can calculate the energy of a moving object. But before we do that, there is two other terms here we need to understand. Work, which is simply transfer of energy when force is exerted on an object. What I wanted to look at is the how to calculate energy, kinetic energy. Before we look at the potential, there is the kinetic energy, energy in motion. You may see in the exam or quiz or homework assignment a question regarding calculating the kinetic energy of a moving object. All right, this is the equation. Kinetic energy is given by what? I have mv square. I have mv square, where m is the mass and v is the velocity. M, all right, this is mass in what? Mass in kg, in kilogram. And you should know what? You should know that 1 kg equals to 1,000 grams. Sometimes you may be required to change the mass, right, from another unit to kilogram, okay? Use appropriate conversion factor. I'm just giving you here an example. If not given, you may need to look at. Now, V, this is the velocity. Sometimes we call this speed, velocity, or what? Or speed of an object. And we have to square that. You need to square that, okay? If it is given in meters per second. So if you are given in kilogram per, I mean in miles per hour, you have to change to kilometers per hour, into meters per second. If you are given the speed in kilometers per hour, you'll have to change the speed to meters per second before you plug it what in this equation. This is an area where you need to recall what you learned in prior chemistry course, those equivalent statements, so that you do what? You do the appropriate conversion. We'll see towards the end of chapter 1, factor label method or dimensional analysis. So remember some of the equivalent statement you may want to recall or go look for it, especially in this calculating the kinetic energy. So if you're given in miles per hour, change to meters per second. So that the reason for that is we will reconcile with the SI units for energy, which is joules, all right, is given, or when you grind the numbers, you'll end up with meters square per second square. So this is an important connection between the units of energy and whatever you will get from this calculation, the calculation you have right there. We have talked about the potential energy. This is just the stored energy, right? Potential energy is the stored energy. Before we look at that, this right here, or I shall have said, this is potential what? Energy. This is potential energy. This is the stored energy. Stored energy. It is the energy possessed by object by virtue of chemical composition. The food we eat has stored energy. We need those energy to fuel our body system, right, to keep us going. Gasoline has stored energy in the chemical bonds for energy, which can be transformed into other form of energy in internal combustion engine of your automobile. It can be converted into sound energy, heat energy, and so forth. So those are just few examples of potential energy. Let's go back to the calculation of energy. There is one example I want to solve, but before we look at that, still on energy, all right. Nutritionists use calorie, which is the uppercase calorie, to mean 1,000 lowercase calorie, lowercase calorie. So if you look at this is the nutritional calorie, uppercase calorie. So any soft drink, if it is 170 calories, That is the the uppercase. In essence, it is 170,000 lowercase calorie. This is what they mean. So next time you order something from Subway and then you see the caloric content, or any soft drink, for example, you see the caloric content, you multiply per 1,000 so that you have a sense of the caloric content of what you are about to consume. Okay. At some point, I was thinking probably they should label the caloric content of food using the lowercase. At least we will be more cautious. This is another conversion relating the joule, which is the SI unit for energy, with the lowercase. You can be required down the line to use that. So this is why what I was explaining to you earlier on, that 1 joule equals to this. That's why we have to change the velocity to meters per square. And remember, you're going to square that. And the mass has to be what? Mass has to be in kg. Mass has to be in kilogram. Well, this is an example of determination of a kinetic energy of an object. This is a baseball weighing 5.3 ounces. What is the kinetic energy in joules of this ball when it is thrown by a major league pitcher at 95.0 miles per hour? One thing later on I'll stress out is the significant figures. If I look at this, why not 95.00 two zeros? Why not 3 zeros? Why not 95 alone? This is to reinforce that your final answer should be in 3 significant figures. So how will you move forward with this? If I had not mentioned earlier on, somebody will say, if I know the mass, all right, I know the mass, so why don't I just plug it in this equation right here? All right, I have m, which you think that this is what I'll be using, times velocity, and then I'll just multiply by this number here, and then half that, and then bingo, you have the answer. That's not the way to approach the problem. And by the way, if it is multiple choice, you will see some numerical value which will be obtained by just doing what I just explained. Plugging in this mass and plugging in this velocity, and then you square it, and bingo, you think that you have, that's wrong. We need to change this to kg by understanding that 1 ounce equals to 28.3495 grams. All right, this is the equivalent statement you need to remember. So if we have 5.13 ounces times, we need to change these to grams, all right? Here's 28.3495 grams. This is 1 ounce, ounce of the code, times 1,000. So that we end up with 1 units or mass in kilogram, unit in mass in kilogram. This is 0 .0 on my calculator. This is 0.145, all right, 43 kg. Please double check that. We know the mass in, all right, we know the mass in grams, so we know that. Next is to change the velocity, all right? If it is 95 miles per hour, it's gonna be, you change that 90, what, yeah, 95 miles per hour. We have to change to we have to change to meters per second, and it turns out that 1 mile, all right, equals to 1609 point what 4 meters. So if I have here 1 mile, all right, 1609.34 meters is miles as we call, and of course 1 hour equals 3600. So we want to get rid of 1 hour here, and 36. So we have our units. This will be, all right, we have 42.46. So now from here, we know this as well. We need to, this is a square, by the way. Yeah, that should be square. So plugging in your equation, this will be a half kinetic energy, all right? Kinetic energy is given by a half mv square, which is a half mass is times 0.145 14543. This is kilogram times 42.468 meters per second. You square this, you square that so that you end up with 131.148. This is kilogram meter square per second square. Remember the 3 significant figures here. So our final answer should be 131 joules. 131 joules. Remember, 1 joule. All right, 1 joule is what I wanted to say. 1 joule equals to kg m square s square. M square s square. So remember, there will be some other units other than what? Other than 5.13. It could be in pounds. How do you change from pounds to kilogram? All right, maybe milligram. All right, you need to look at those other units used in measurement. The speed also could be in other units other than miles per hour. You need to be able to do dimensional analysis, plug it in the equation, and you have yourself the kinetic energy for any given object. All right, any given object. We will take a break and come back to numbers where I want to start from section 1.5. All right, we'll look at the units of measurement. We'll define a measurement. All right, numbers in chemistry play a major role in. All right, numbers play a major role in chemistry. Many topics are quantitative, you quantify, that means there must have been some numbers, numerical. We'll come back again and look at the numbers. Just take a break and we will come back. Thank you and see you. I'm gonna stop sharing my screen and end the session. See you soon. Thank you.